The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
It's my pleasure to be here. I appreciate the SD Council and ACI invited me to come. I've talked about curing before at ACI, and I'm just going to give you a pavement designer's point of view and specifier. I've had a lot of interest in this over the years as I've realized that curing and effective curing affects the life of a pavement structure, and I'm talking about a concrete structure, of course. It affects it in many ways. And so I'm going to go through a little bit on what some of the issues have been with present curing technology and try and, at least from a pavement design point of view, why we need to monitor and why that would be important and what the approach is to monitor curing. We have an ongoing study funded by the Texas Department of Transportation, and I'll give you a little bit there on what the results been and what development we hope to get from that. First, just to point out that the current ASTM is really focused on moisture loss, and of course there's several limitations associated with that. Trying to translate the rate of loss and so forth under field conditions is not an easy thing. Also, when we have new technologies coming on board, how do we evaluate those and make use of them and effectively employ them under construction? And then finally, what if we're going to try to measure curing quality, how do we define it? I mean, that could be another interesting topic. There's also the time and rate of curing. Hardly ever discuss that, but I found it to be a very key factor, particularly on performance. It's not just concrete strength, but it's other performance issues that are associated with that. The duration of curing in the set gradient, I'll point out why that's important and why I think curing is affecting this. And then trying to represent all these factors here in terms of total moisture loss, I think, is a very difficult thing to do. We look at the construction methodologies and how do we control equipment. Somebody's making a decision there on what kind of pressure, what kind of rate the equipment's going to move, and how quickly it's going to place a curing compound. As a specifier, do we just copy the ASTM and put that in there? Does that work? I've seen that done, and it's not particularly effective. Do we just monitor how much is put down? And can we do that? There's industries that have ways of checking that. And then, what about the contractor's motivation? What of the idea of paying the contractor to actually do this? These are some things that I think we need to start thinking about, especially with new methods and materials. We've got the old methods that we've known about for years. Again, how is the best way to employ them and to check the quality that we get? And a lot of times it shows up in the end product. And one here is tool lift placements. That's a huge issue. Jeff or someone mentioned the RCC. Big problem in RCC is getting the two layers to bond together, and I think it has a lot to do with the curing. But I've asked this question before, why cure? And to me it's, why should we monitor? Okay. Yes, strength is always a key thing, but I think it's more than that now. And one here is this problem here. This is spalling. And this, of course, is a very shallow type of distress, but the method of repair is usually some material here that's got to bridge a crack, of all things, which is difficult enough to do, but the placing, pretty intensive, and that's not to mention the cost of the material. And then the problem here is that they're not lasting any longer than conventional methods are. And so, what can we do in that regard? That's another one. But curing, involves moisture, temperature, and time. Again, one of the real challenges is how do we place bonded overlays and get them to bond? Or how do we do the same thing in two-lift construction? Recently, I've really seen a lot of issues here, and what we're dealing with is a stress pattern that's developing in the top layer. And this is a very interesting pattern. It's difficult to deal with, and if we don't bond it, then we're going to get a lift-off there. And that can get ugly too. Here's a photograph from an airport that I won't mention where the bonded overlay did this. The red area is the separated area. And we used an ultrasonic machine here to find out where this was, but you can very quickly do this with a hammer. and you can get pretty good with a sledgehammer. Another thing in the pavement area, it's a huge thing now with the mechanistic design, is how to deal with this here. This is the erosion problem. And what I'm finding is that once we get the concrete slab in this configuration, once it does that, it's going to start wearing on the base layer. And if we destroy the bases underneath the concrete pavements, that is a sustainability problem big time, because we have to remove and replace. That's an issue. If we can figure out, and again, I believe this is the set cure here, or the set gradient is affected by the cure that's affecting this here. I've seen some pavement sections that don't do that, and they perform pretty darn well. There's a need to understand how we're curing and what to do to better employ it to get better performance. But evaporation factors, we're all familiar with this, and wind speed, temperature, and relative humidity. These all have a play, and I've looked at performance data for many years. I've spent a lifetime studying that for concrete pavements, and it's inevitably a cloud of data here. Okay, it almost has no trend. Here, we're the design engineer, and we're trying to fit our performance curve in that. Okay, it hasn't always worked out well, and still, at one point, I started looking at environmental effects. And I did the best I could to get degree day data on the constructed project, but it was interesting how that mass of data started to fit a pattern. And it's a real testament, and I believe it's curing here. That is one of the big things here that we're seeing in this. So from a pavement point of view, we want to know how to predict the life. And the very key part of that is that little factor right there, that R factor. That's a stress ratio. And it's the stress in the concrete divided by its strength. Well, that stress is often made up, and it is in most design procedures, of the stress due to loading. Okay, that's the mechanical loading. And then we have this environmental part here that comes in. And we're doing this in the MEPDG, and it's in two pieces. We've got the curling and warping part here, that's where the slab's moving and lifting off and settling down. Then we have the built-in part. I think that's directly a curing effect there. We're seeing it in national methods of design now. We're not sure what to do with it, but I think there's a role here. In some of the simulation studies we've done of curing, which is something I've been involved with as well, I'm finding that the set gradient is changing throughout the day. It changes with time. It's not constant because our weather conditions aren't that way. So what do we do? I mean, can we adjust for that? That's really what the question gets down. And to get to that, we're going to have to monitor and manage. Now, here's the interesting thing. You can show this to yourself in the MEPDG, but we don't want a zero gradient, by the way. We want a little bit of pre-stress that's built into it. And so we're not looking just to zero it out. We want to control it. And we found that if we have a little bit of gradient, we can lengthen the life of the pavement. We can cut the design thickness down. So very interesting situation here. So looking at the effective curing on set, I think that's some area that we need to start looking at and getting into and seeing how the method of curing can benefit us and affect the way the set gradients are forming. And there's all kinds of weather conditions out there that we're paving under that affect what that set will be. It's beginning to get a lot of attention, I think. All right, so the new approach here, just to go through some of the detail here, we're using a miniature weather station. Actually, it's a miniature maturity meter. So it's measuring everything that you need for maturity plus the moisture, and we're doing that basically with chilled mirror sensor technology. Very expensive, but very accurate, very repeatable. I've used it for many years and done quite well with it, but we can get the humidity out of the information we get from the sensor. We use that in a couple different ways. We're recording the humidity in two chambers, and this is a base plate that you see right here that is actually divided in two separate chambers or isolated from each other. This one is sealed, this is filtered. So the effect of the curing is represented inside of that chamber there that the sensor is monitoring. So we're picking up relative humidity in two very different conditions. One is sealed here, the other one has a curing membrane over it, which is protecting it to the extent that it can, from the ambient condition. Here's a close-up, the way we do it in the field. Here you can see the top of the base plate again. This is a wire mesh. I just use a mortar, a very thin mortar, as part of the filter. And this, of course, supports whatever curing technology I want to use for the most part. I can put clear curing compounds on, or pigmented or whatever on that, and it worked out very well. So these are the monitoring ports here where we put the sensor in. Now we can do this in the field or in the lab, and that's a good thing about this protocol. It bridges the field and the laboratory condition. And so the technicians can prepare the top of the plate, lay it on the surface of the concrete, get it ready for spraying. So the spray machine comes over and sprays it as it normally would. Leaves a bare spot, of course, and that's where we set up the base plate. Here, you know, the curing comes off and sprays over where you have it set up. So this is what it looks like when it's in place. And this, again, is measuring weather conditions, but mainly humidity and temperature is what I'm interested in. This I'll talk about in just a little bit, but that's a point to collect dielectric data, and I'll explain that momentarily. But this is typically what the data looks like, and this is a sealed trace. Right here is the filtered. Notice how they tracked each other for a while, but they finally separated. That's where I think the curing is, the membrane or the protection is beginning to diminish quite a bit. You know, it's not all the same for different curing compounds. They're not all created equally. That's the ambient condition that we're running the test under. I'm calculating a maturity for this now, and I think this is the best use for maturity that I've ever come across. It's early age, and it's done under a sealed and a filtered and an ambient condition. I get 3 different maturities from that over time. So this is over the period of the time the curing of this is determined. These calculations are used to get a single index that I call evaluation index. And so I try to represent the entire condition of the curing through this EI term here. This is a plot of some of the data that I've gotten in the field. You'll see here, this is an RCC. And Jeff, you brought up an interesting question, you know, can you put internal curing in RCC? Well, look at this. This is very dry. Okay, right there is the EI. And it's running at about 50%. Now, in my experience, and what I've done with this, you got to have an EI of at least 80% if you're going to do decent curing. Now, RCC is really open. It's got a very open texture. At least that's what I've traditionally seen. But you know, nowadays they're changing the way they pave RCC. They're really trying to close the surface up. And I think that's going to be a huge benefit. But why does it separate on 2 lifts? And I've visited enough RCC to know that that is a common issue with 2-lift paving, is trying to keep those layers bonded together. And I think it's got a lot to do just how much drying is going on at the surface. Here's a resin cure that was done under a different paving condition. But I want to point out right here the surface humidity. Notice how it breaks off right there. That was within hours after placing it. It did that. That was the same day it was placed. And as far as I could tell, it failed right there. Now the next day, after it went through the evening humidity changes, it was okay at night. But about 10 o'clock in the morning, look what it did again. It broke again. That's not good curing. And it ended up being finally reflected in the EI right here. This is a lithium cure, which, by the way, is not an ASTM-approved curing compound, but I found it to be extremely effective. Now, early on, it lets a lot of water through, but later, I've seen it really be very protective. And I think that's kind of what we need in a pavement structure, is curing the following day after placement. I think that's when a lot of the issues take place. Now, I mentioned this dielectric constant point. We've used a device, a percometer. It's a miniature GPR to measure dielectric of the surface material. And I've done it here at a point, just at a very small point on the surface of the concrete. And I'm doing great, by the way. I'm way ahead, so I appreciate that. So anyway, what we found with these readings is a trend in dielectric with time for almost any curing situation that follows this here. And we've taken the slope here, this is what the alpha is, and we've checked it against the moisture losses that we measure in the lab. And we're seeing some correlation there. What we're trying to do now is tie the EI to that slope. Now, why am I interested in this? Because the device here, which I got a picture of it someplace, is fixed. It's a base station. So we got to get to other areas of the project in order to really get a good picture, right? You know, get a good picture of what the curing is. I'll talk about that in just a second. But anyway, in our test program, we're looking at trying to build on this database here. We're testing more curing compounds, more curing situations to try and validate what we're finding. So in the lab, we have, here you can see the device, different wind speeds, and we can get the weight loss. We're checking abrasion resistance. We're doing all those kinds of tests to check, again, the quality. And here's an example. Ignore the name here because I meant just put ABC compound, but here is a characteristic curve from the lab of where we're showing EI over time, and we're doing it for different rates of application. Now for a protocol in the field, I got to be able to come back to this curve and use the EI that we determine under the field conditions and check if the rate is adequate. And that's how we could adjust the rate under curing conditions. Here's another one, and these are two commercially available products. Now, do they look like they're equivalent? No, they're not, but the manufacturers are not telling us that. And I think we need to start recognizing that as well. Here's another one that held pretty well during the curing. So there's a range here that we're seeing, and we can pick this up under the lab conditions. We've done, like I say, weight loss tests and moisture tests, or moisture loss tests, and then we've done the abrasion tests with it. And we're seeing pretty good results there. We're going to continue to do this. Some of our early data was a little scattered, but as we get more data, we're getting better trends, I think, of abrasion and moisture loss versus the EI. So we're hoping to improve on this as we go. But so far, it looks pretty good. Now, from our lab program in the field, where we set up, again, you can see the device here. We're getting in the field the humidity and EI information, plus we're getting the dielectric. And again, this is the trend here. And we're fitting that trend with a characteristic mathematical equation to get the slope data. You can see the slope data here. We're looking then to expand on the ability to get the GPR. Now this is how we're doing this. A lot of research at TTI has been looking at using ground penetrating radar to get densities, moisture contents, what have you. We thought we could use it for curing, and so we had this little cart in the lab. You notice the antennas right here? And then we've got the computer here that records the data. Now, this is air-launched, and we're shooting through the compound and the concrete now. So we're not using this little protective cylinder that I've used in the past, and so we're looking at how well we can do that. Now, we ran the machine here down the alignment a few times to see what it would do. I wasn't sure what we'd get, but we got pretty good repeatability here. Here is a trace. Now, there's a couple things to pick up here. Notice, first of all, how jumpy it is. I think that's an indication of variability, okay? And I think that would be a good way to spec a job and see a minimum variation there in the trace. Now, we did this 3 times, and you can see we got really good repeatability with this. I was amazed how we were able to do that. We also checked it at different times. We started seeing the change as the moisture was evaporating from the surface with this. Here's another shot, and I understand the curing looks like bad here, okay? But I didn't care. I was just the innocent observer here, just watching what they do. And so we thought we'd jump in and check it where we could. But look here, they sprayed it twice. It shows up right there on our trace. Otherwise, a lot of variability in there, okay? And this is one thing that we could probably improve on, is getting better consistency. Here's another shot. 2 hours and then 60 hours after placement. We're seeing a steady change there, as we would expect, as you see more water being evaporated from the surface of the concrete. So taking all the data at one position over time, we can get this characteristic slope then, okay? And we can use that slope then to go back. This would be the field curve, right? So we measure the EI in the field at a given point, and we use data from all over the site to build up this chart here. And we can take the EI and come in and see what our level of application should be. We can adjust it on the run that way, I think. This is what I'm anticipating. New protocol. I think something like this is going to be key to the ability to start managing curing. And I think this is something for the ACI committees to start talking about. What are the protocols to manage a curing for a project? I think that'd be an interesting thing to start really discussing and getting into. And then what are the protocols to monitor it and to track how the management should be and what the strategy is. We're using NDT then, and the EI seems to be very practical for field, for lab use, and really importantly is computer simulation. I use it to characterize numerically the interface between the ambient and the concrete material. I think it's a very important thing to be able to do. Besides the temperature effect, we have to be able to account for the moisture and the humidity effect in there. We have found that the GPR, either with the percometer or with the air launch, is very repeatable. and is sensitive to things like application rate, curing time, and uniformity. I think the very key things that we need to be able to pick up. Lastly, I want to say, I think this system is very amenable for automation and computerization and mechanization, anything you want to call it. Think of the project now. By the way, we're paying the contractor to do the work, right? We're going to pay him. And we're going to control the paving or the curing by GPR and a base station and curing referencing curves, and all according to the climatic conditions. We're almost 3D printing the pavement here in terms of curing. I think that's where we have to go, and that's what I hope to go in our research project. This guy here, okay, he's sleeping. We won't even have to change what he does. All he's got to do is come to work, flip the switch on, and he can spend the rest of the day sleeping, while the rest of it takes care of the curing operation. And we got to avoid this. This is an example, I think, of very bad curing. It happens. That's the problem of it. So anyway, those are my thoughts and kind of what our direction is and where we want to go. But anyway, I appreciate the time.